Let's look at one of the first topics that frighten people about C. That's pointers. The syntax scares people when they come across it for the first time. So it frightens software engineers, it frightens quality managers, it frightens safety testers. In automotive applications and safety critical applications, they hate the idea of pointers. Now, pointers are just memory addresses. But that's the problem about them. It's a memory address, but how do we know what's at that memory address? How do we know that memory address is valid? There's all kinds of problems. That pointers are very powerful, but that's where the problem lies. They are almost too powerful at times. And one of the things about pointers is that you're never quite sure that what they're pointing to is valid. So what you'd really like is a guaranteed pointer, so that you knew that it was going to be valid when you wanted to use it. No worries at all in that pointer. And that's where we have the idea of a reference in C++. Now, we'll be familiar with pointers in C. Now, we've got a very simple piece of code here that we've got two pointers being passed into this function f, and we just do one assignment to the other. And that's the reason why we pass them in as pointers in the first place. So as not to copy the values into the function, but we've actually got pointers to the variables, and that means I can modify b in here by taking the value of a and putting it into b. And that's all done through pointers. So we pass in the address of the variables j and k. They go into the function, and then it means I can basically assign the value of j into k in the function. Well, references are the C++, possibly could say, preferred way of writing this code. Rather than passing a pointer, we do it by references. And having the ampersand here turns this into a reference argument. So rather than passing by value, which would be that we would just copy the value of j into a, that would be the normal way that it would be done, we're going to pass a value in, a reference in. And that reference to the compiler is basically an automatically managed pointer. To us, we can think of it as just another name for the variable. So here we've got j, and that name j refers to an area of memory somewhere. Well, through the reference, a also refers to that same area of memory. So you can imagine that a and j are the same name for the variable. So whatever I do to a also affects j. Whatever I do to b also affects k. And so now I can do a direct assignment of b into a. And you could look at that and you could say, okay, that's more or less the same. What advantages has that given me along the way? Well, let's consider what you would really do in the real world. And what you should do if you've got safety critical code and so on, and well written code, is you really ought to check that these pointers are valid before you use them. So we would check to make sure that a and b are not null. There's all kinds of other things you might want to do as well, just to be guaranteed that we're not trying to use invalid pointers. Because there is nothing stopping you passing in null pointers or something wrong over here. With a reference, the compiler manages that process. The compiler will not let you pass an invalid reference. There's no such thing as a null reference in C++. You always have to refer to something. So it's an implicit check that your code is going to be valid, your pointers are going to be valid. Now, as I said, the compiler treats references like pointers, and that's its internal mechanism for working with them. But they are checked pointers, if you want a better way of looking at it. So what does that do to our code? Now, going back to the compiler that I used before with the Hello World example, when I put through the pointers and the reference code, they were exactly the same size. So it doesn't matter whether I had the pointer code or whether I used the references. It was the same output size. But of course, you would want to, in real-world code, use checked pointers, make sure they're non-null, all that sort of thing. So while you could argue that references have not given us anything directly, what they've actually given us is the ability to not have to have the code for checking that the pointers are valid before we use them. So there's no code overhead of references over pointers, but it saved us a bit of work. And that's going to be a bit of a theme as well when you look at C++ in detail, that C++ can automate some tasks for us. It does that through the class mechanisms and so on. And that's something we can take advantage of. Not having to check a pointer is a real bonus. That means that there's less code for us to do. The pointer is still checked, but it's checked now at compile time. It's not checked at runtime in your program.
Doulos is a training company providing expertise and specialist training worldwide in all of the areas you can see on screen, from SoC design and verification, FPGA and hardware design, to embedded software and Python and deep learning. You can watch the rest of Des's webinar, Embedded C++, Dispelling Myths and Preconceptions, whenever you want, by heading over to our website www.doulos.com/od and registering for free. For more free tips and tutorials, visit the know-how area of our website, and don't forget to subscribe to our YouTube channel. Thanks for watching.